much, for your nice introduction. And yeah, so let me got it. Yeah, and yeah, thanks for remembering the meaning of this so-called MP3M. Even me cannot correctly remember what does that mean. It's kind of, yeah, the name of it is a little bit confusing, like the password. But anyway, it's a multi-messenger organization that has been included several institutions and national labs and the university. So, okay, hello everyone. My name is Zidu, and as Shilin said, I'm an MP3M postdoc working at University of Tennessee, Knoxville. So today is my pleasure to discuss with you guys here. And I think I have a very difficult job today. My job today is try to convince you guys that there might be some new indications of the strong phase transitions from our existing nicer observations. So let's begin. So first, obviously, we are talking about neutron stars today. And in my own opinion, almost all the questions or all the studies about the neutron stars can be roughly classified into three types of the questions. So the first question is what's inside a neutron star? And the second question is that what can we actually observe about the neutron star? And then the third question is that how are those observations and the inner components of the neutron stars relating to each other? So these are the third question. And in this talk, to be more specific, we are going to ask ourselves a little bit more detailed question. And the question that we are going to ask ourselves is, are there any quarks inside the neutron stars? So to answer this kind of the question, the observations that we are going to use are actually the masses and the radii of those measured neutron stars, and how those kind of the masses and the radii are going to relate with the existence of the quark phase inside the neutron stars. So they are relating to each other via the so-called the equations of the state and the TOV equation. So basically speaking, this so-called equation of state are just the neutron star matter pressure as a function of the neutron star matter energy density. So that's the so-called equation of state. So given the equation of state and the very reliable TOV equation, you can construct any kinds of the neutron star masses and the radii. And of course, up to now, probably it is still not very clear for us how these three things are going to relate with each other. So I'm going to explain this kind of the relevant relationships one by one. So the first relationship is between the equations of the state and our observations, which are the masses and the radii of those neutron stars. So how they are going to relate with each other? So it has long been realized that as long as we know the complete information of the neutron star radii and the masses, for example, if we have a complete mass and the radius curve of the neutron stars, then we can model independently and precisely reconstruct any kinds of the equation of states. But of course, that is the very ideal picture. So in the real world, we can never do that because realistically, right now we only have a few measurements of the neutron star radii and the masses. And all those measurements have very large uncertainties. So it turns out that based on that kind of the finite number of the measurements and the relatively large uncertainties, what we have are just a probability density distributions of those equations of the states, and also the probability density distributions of the masses and the radii of those neutron stars. So how to get this kind of the probability density distributions? So this kind of the PDF distributions are obtained from the so-called Bayesian inference. So the Bayesian inference, I guess probably all of us have some kind of the knowledge about that. But anyway, it is a statistical method. So which means that based on a finite number of the observations with uncertainties, then we would be able to obtain a posterior distribution of the equation of the state and also the mass and the radius curve of those neutron stars. So, for example, this is those are figures from a recent paper. So, when the authors are going to do this so-called Bayesian inference, so we need to remember that the Bayesian inference is still model dependent, because when you are doing the Bayesian, you need an underlying parameterization of your equation of states. And here, for example, that kind of the parameterization in this left-hand side panel, they are relying on polytrope piecewise equations of the state at high density. And on the right-hand side, they are relying on speed of the sound piecewise equation of the state, representing the high density equation of states. So why we can only use that kind of the naive parameterizations? That is because at higher densities, we know almost nothing about the equation of states. We don't even know what's inside there, if there are quarks or hadrons or something else. We don't know about that. So the only thing we can rely on are this kind of the naive and the straightforward piecewise parameterizations. Oh, sure. Yes. Thank you, Shirin. Okay, great. Okay, so you see that when you are using different parameterizations for your high density equation of state paths, the PDF of your equation of state as well as the MR curve of your as well as the probability density distribution of the MR curve also behave a little bit differently. And so does this one. This is also a recent work about a Bayesian inference of your neutron star equations of the state and your neutron star mass and the radius curve based on the Bayesian inference. So yeah, so after all, this is how your equation of states are relating with the MR curve. So to conclude, if you know all the information about your MR curve, then you can reconstruct your equation of states precisely and model independently. But if you only know few observations of your neutron stars masses and the radii, then what you can do is just to infer a probability density distribution of your equation of states by using the so-called Bayesian inference. And that Bayesian inference is model dependent because you have to choose an underlying equation of states parameterizations. So that's about this kind of the relationship. Then we go to the next relationship. How the existence of the quarks are going to relate with your equations of the state. So, okay, if we want to rule out or confirm your existence of the quark, what should we do? So usually the smoking gun for the existence of the quark is the so-called hadron quark phase transitions. So for example, if a detection of the hadron quark phase transitions means that there might be something different after that kind of the phase transition. And that something different is your quarks. So, okay, and of course, then we need to ask ourselves how to detect that kind of the quark hadron phase transition. So there are a lot of theoretical predictions and the descriptions of the hadron quark phase transitions. And here, probably, if we want to have a reliable and a realistic detection, we need to first discuss the most distinguishable type of the hadron quark phase transition. And that is the so-called first order phase transition happening here. So as we can see there, when you have this kind of the first order phase transition, on your equation of the state, you will observe that at this kind of the transition pressure, there will be an obvious and abrupt energy density jump in your equation of the state. And this energy density jump is an illustration of the appearance of your hadron quark phase transition. And then when you introduce this kind of the first order phase transition, correspondingly, you will see that depending on the magnitude of your transition pressure and the strength of your energy density jump, you will have a lot of strange shapes of your neutron star mass and the radius curves. But anyway, when you are introducing this kind of the phase transition, what you will see is that your M and R of the neutron stars will experience this kind of the sharp turning point. And this kind of the sharp turning on your MR curve might be an observable signal of the phase transitions. And if you have find that kind of the phase transition, then probably you can say that after the phase transition, there are quarks inside our neutron stars. So that's a very simple logic behind it. So up to now, it seems that everything is fine, and we have phase transition. We have the corresponding possible observables for that phase transition. So what's the problem over there? So the problem over there is that all of those kind of the phase transition features are local features. And these are very detailed features over there. And we still need to remember that up to now, we only have a few real neutron star observations. And all those neutron star observations have relatively large uncertainties. So the question is that how to search for such kind of a local detailed feature in your very obscure picture of your equations of the state. So that's the current problem. So how usually people are doing that? Of course, I'm not the first one trying to answer this kind of a question. There are a lot of good works discussing the searching for the phase transition signals. So how usually people are doing that previously? So usually the people are using this so-called Bayesian factor to infer the possibility of the phase transitions. So of course, then we need to ask, what is the Bayesian factor? That kind of the Bayesian factor is defined as that. It's a ratio of two probabilities. So on the upscales of the ratio, it's the marginalized probability of your observed data based on a theory or hypothesis with phase transitions. And on the downscales, these are the marginalized probability of your data based on the hypothesis without phase transitions. So these are two marginalized probabilities, and this Bayesian factor is a ratio of these two factors of these two numbers. So which means that if this Bayesian factor is much larger than 1, then it means that your observables is preferring a hypothesis with phase transitions. But if that Bayesian factor is much smaller than 1, then it simply means that your observable is favoring theory without phase transitions. But yeah, as I said, we have only a few observations, and all of them have large uncertainties, which means that this Bayesian factor now can be much smaller than 1, or equal than 1, or equal to 1, or somehow, or sometimes obviously bigger than 1. So briefly speaking, everything is possible. Nothing has been ruled out yet. So we can say there are phase transitions, or we can say there are no phase transitions. They all agree with our current observables by using a Bayesian factor. So now, in this talk, we are trying to ask this kind of the question. Is the Bayesian factor the only indicator of the appearance of the phase transitions? So that's the question that we want to ask in this talk. So what might be the answer? So, okay, so let's first jump out from the neutron stars and look at something totally different, which are the neutron skins of those nuclei. Okay, I know that this might be some kind of a strange jumping, but honestly speaking, I'm talking about the neutron skins of the nuclei because this method that we are discussing now is inspired by our discussion of all those neutron skins. So, okay, neutron skins. What are the neutron skins? The neutron skins are simply the deviation between the neutron radius and the proton radius in a neutron-rich nuclei. For example, in the calcium-48, you have 20 protons and 28 neutrons. Then the neutron radius of your calcium-48 is much larger than the proton radius of that calcium-48. And then the deviation of the neutron and the proton radius will be the so-called the neutron skin of the calcium-48. And so does the net fuel rate. Okay, so almost 20 years ago, we know that this kind of the neutron skin is strongly correlating with the radius of a neutron star. And that is understandable because both the neutron skin and the neutron star and the radius of the neutron stars are actually controlled by the same equations of the state. And it is actually the symmetry energy profile of that equation of state that determines both the neutron skin thickness and the neutron star radii. And after 20 years, the study of the neutron skin thickness has made such a big progress. We not have only measured the neutron skin of a specific nuclei, we actually measured 2 of them. So now we see that this vertical line that number is a value closely relating to the neutron skin thickness of the calcium-48. And the number on the horizontal line is closely relating to the neutron skin thickness of the lab 208. And if we are doing this kind of a 2D plot, we see that all the neutron skin thickness from these 2 nuclei from the theoretical models are now somehow dropping on this kind of a linear line. So you see that the neutron skin thickness of the calcium-48 and the neutron skin thickness of the lab 208, actually they are obviously correlating with each other. And that kind of linear correlation has been observed by both the relativistic models and the non-relativistic models. And to make this plot more interesting, we also have the corresponding observations. And that observation are made by a recent P-Rex2 measurement for the lead and the C-Rex measurement for the calcium. So these 2 measurements is represented here by a big contour over there. Okay, so now we have theories, we have experiments, and we see the linear correlation of those theories. So what's the problem, or what's the interesting question for this kind of the figure? So the question over there is that when we see that kind of the obvious linear correlation between the neutron skin thickness of these 2 nuclei, we might be wondering, or we want to ask ourselves, how strongly actually are the 2 neutron skin thickness correlating with each other? Is that kind of the correlation model dependent or non-model dependent? So what's the true strength of that kind of the linear correlation? That's something we are still wondering about. And then when you go to the neutron skin measurements from experiments, it's obvious for us to see that this kind of the experimental measurements is somehow a little bit deviating from our linear correlations of these 2 neutron skins predicted by our theories. Then we might be wondering why this kind of the experimental measurement seems to deviate from our theoretically predicted linear correlations. So that's the problems. And it is still the problem. We are still working on that. To conclude, it is still a puzzle. So I don't have answer to that. And remember that today we are talking about neutron stars, not neutron skins. The reason why I'm talking about the neutron skins is because we can ask similar questions to neutron stars. So the first question, how strongly are the radius of these 2 neutron stars correlated? The first radius of the neutron star we are interested in is the one with 1.34 solar mass. And the second neutron star radius is the one with 2.0 solar mass. How strong are these 2 neutron star radius correlated? So that's the first question that we are going to ask ourselves. And then the second question, we know that the reason why I choose these 2 neutron stars with that specific mass is because we do have some measurements for the radii of these 2 types of the neutron stars. We have 2 nicer measurements. And then we will be wondering if that 2 nicer measurements still obey the linear correlation relationship that we expect to find between those 2 neutron star radii. If there is a deviation, just like what we see here for this kind of the neutron skin, then do we have any explanation for that? So that's the question for us. Okay. So now let's go to what we are trying to do in this project. So if we are trying to if we are trying to ask ourselves if there are correlations between the radii of these two neutron stars, then first we should make sure how much do we understand about the expected correlation. If we don't know what should be expected, then there's no way for us to distinguish such kind of the correlation and do further quantifications. So what should be the expected correlation? So to somehow characterize that kind of the expected correlation between the radii of the two neutron stars, we are trying to find two extreme cases. Because if you want to characterize a linear correlation, then it is simply a linear regression. And to specify a line, you just need 2 points. So what might be the most important 2 points that we can study to characterize that kind of the linear correlation? That's 2 extreme cases are the maximum radii of these 2 neutron stars and the minimum radii of these 2 neutron stars. So if we assume that the maximum or the minimum radii of all the neutron stars are corresponding to the same Steve or the Slope equation of the state, then we will be able to see that all the possible distributions of this kind of the points, where the x component is your radius of your smaller neutron star, and the y component is the radius of your bigger neutron star. Then we will be able to see all the possible distribution of this kind of the points will be lying between these 2 extreme cases. And if you expect a linear correlation, then probably you want to characterize a so-called linear regression. And that kind of the linear regression should be approximately characterized by a line joining these 2 extreme cases. So which is understandable, just like the neutron skin. Sorry, I'm talking about neutron skin again. So when you see the neutron skin, if you are gradually increase the so-called symmetry energy slope, then you will see that both the neutron skin thickness of the calcium and the lead are increasing simultaneously. So do the neutron star radii. If you are going to increase the stiffness of your equation of the state, then you are going to see both the radius of your smaller neutron star and the bigger neutron star increase at the same time. But you cannot increase forever. You have to have an end. And that end will be this green extreme case, where you meet the maximum radii of your 2 neutron stars. And of course, you cannot decrease your stiffness forever. You have to have a start. And that starting point will be this blue star representing the minimum radii of these 2 neutron stars. So that's a very naive idea behind our characterization of the expected linear correlation of the radii of these 2 neutron stars. And actually, this kind of the linear regression can be expressed very easily and analytically. So you see that this is the relationship between all the neutron stars with 2 solar mass and all the neutron star radius at 1.34 solar mass. So they are related with this kind of very simple equations. It's a linear equation. And probably the most interesting information is about the slope of this kind of the linear regression line. So you see that this slope, so it's actually a function of the mass gap between these 2 neutron star mass. So what will happen if the mass of these 2 neutron stars are the same? Then you will see that the slope will simply become 1. And when it becomes 1, this linear regression will simply because the deviation between the 1.36 neutron star radius and the 2.0 solar mass neutron star radius. And that kind of the radii deviation between the 2 neutron stars is actually a very commonly used value to characterize the mass and the radius distributions in our current understanding. So you see that this linear regression that we are proposing here is a generalization of this neutron star radii deviation. Okay, So then you might be wondering, where does the maximum and the minimum radii come from? It's not coming from this work. It's coming from a recent study about the maximum and the minimum radii. When those guys are trying to study the maximum and the minimum radii of the neutron stars, they are trying to do that with minimum model dependency, which means that for those equation of state below 2 saturation density, they are using the chiral effective field theory to constrain those low density equation of states. And for the equation of state above 2 saturation densities, they are just connecting their chiral equation of states with the causal equation of states, with or without the phase transitions. And in this way, they can construct several branches. And this red branch is representing the maximum radii of the neutron stars. And this gray branch is representing the minimum radii of the neutron stars. And as what I said, this maximum branch and the minimum branch of the radii is actually corresponding to one single extreme equation of the state. So okay, just want to let you guys know, where does the information come from? They come from a study with a minimum model dependency. Okay. So after we have figured out what should be expected, then we will be prepared to answer such kind of the question. Will there really be correlation between the radii of the 2 neutron stars? So the answer to that question actually depends. It depends on what kind of the equation of states parameterization that we are choosing. So for example, in this kind of the standard scenario, we are using two types of the equations of the state parameterization at higher densities. And those are the polytrope parameterizations and the linear parameterizations. And all of these parameterizations are piecewise equation of states at higher densities. But at lower densities, they are still constrained by physical information, such as the chiral interactions or something like that. It's just like at higher densities, we use 3P and 4L parameterization. And when we are using such kind of the parameterization, and then we do the Bayesian inference. After our Bayesian inference, we will then be able to extract the posterior distribution of those neutron star radii points from our Bayesian inference. And then we just simply put them in this figure. As we see, the red contours are the density distribution of our neutron star radii points from the 4L model. The black points are the posterior distribution of our neutron star radii points from the 3P model. And then we compare this kind of the density distributions with the expected correlation that we discussed several pages ago. So we see that, yes, they do have a very obvious linear correlation. And that kind of the linear correlation is agreeing with our expected correlation very well. So that's what we see if we are using this kind of the standard equation of state parameterization. And if that's still the case for our NISA measurements, will the NISA measurements fall here? Will the point from the NISA falling here? If it is falling here, what does that mean? So that is what we want to understand. Okay, but anyway, before that, I will just show you what's the corresponding probability density distribution of the equations of the state and the mass and the radius curves from our standard equation of state parameterizations. So the conclusion is that those kind of the PDF distributions are quite reasonable, then they are already able to explain all the constraints that are considered by this kind of the Bayesian inference. Okay, so these are the NISA measurements. So on the left-hand side, what I am showing you is the probability density distribution of these 2 neutron star radii distribution points, of these 2 neutron star radii points distributions. So this color is representing the likelihood, it's representing the value of the likelihood suggested by the NISA. And if you're comparing this kind of the nicer likelihood distribution of these two neutron star radii, then you will see that obviously it is, I mean, part of them is falling within this kind of the linear band that we expect. But still, there are about half of them are somehow falling outside of the expected linear regression. So how do you explain that? For the neutron scale thickness, we have no good answer to that. But for the neutron stars, we do have answer to that. Because in neutron stars, I mean, the equation of state are ranging from low to high densities. There are so much possibilities that you can imagine. For neutron stars, we just remember we are talking about the phase transition. If you are introducing a phase transition, then you can easily make some points like that. So this is the radii of these two neutron stars produced by these so-called CSS models. And these CSS models includes the strong and the sharp phase transition in it. A question? Yeah, sure. Yeah, right here.
So if you diagram the right,
that
one, I think construction curve where a star with bigger mass will have bigger rate.
Right.
But I can see construct an equation state where a bigger mass will have a smaller rate.
Yes.
All of them seem equal.
Yeah. So that's a good question. So that is because in this kind of the figure, we are only see the band of those equations of the state, right? So, and that is always what I am trying to emphasize, because this is the band, but actually to see the correlations, you need to make sure that the points that you are making are based on the same equation of states. So because this is the band, but it doesn't mean that you can randomly connect any points inside that band. You cannot do that because there are always the correlations between those points inside, but those are the missing information inside this band. Some of the equation of state are like this. Okay.
Bigger mass means bigger radius.
Right. Some of them, yes. Yeah, bigger mass in bigger radius. Yeah.
The left of the next one. The one that you have, the other one, that is connecting to radii.
Now, which one, right? Yeah.
It seems that every model that you have considered, the bigger mass means bigger radius. Is that the case for all the equation of states that you work with that?
It's not always the case, right? Because we need to consider the vertical line and the horizontal line. So sometimes, for example, here, those are the bigger mass for smaller radius. Yeah, because the horizontal line is the radius of a two solar mass, and the vertical so the vertical line is the radius of a two solar mass, and the horizontal line is the radius of a smaller radius. So for example, if I am pointing out here, then it means that your two solar mass has just a radius of 11 kilometers. But correspondingly, you have a 1.3 solar mass neutron star, which is bigger than 11 kilometers.
Okay.
Yeah. Yeah. Go outside.
are not considered realistic, I guess. So then there's, without those, you don't have a tendency that to be behind another class.
Okay, so let me try to understand you, sir. So
okay, so let's say we have over here, you have figure you have 60 kilometer.
yeah,
values corresponding to 50 kilometers. There's nothing.
yeah, of course, yes.
On the right hand side, that I haven't seen saturated.
Yeah, right. Yeah. Here there are nothing there. Yes. So right, nothing existing over there. You are totally right, sir. And that's why we see that if we are look at realistic Bayesian inference, all the posterior distributions are following on the lower side, not on the upper side. On the upper side, we have no observations. And if you are considering the observations, then the Bayesian are going to tell you what are the radii corresponding to the observation, and then they are falling over there. So here, yeah, I think it's just my fault of making a too large figure, but actually over there are nothing over there. I should cut off the upper side of this figure. Yeah. There are no. I mean, if we are focusing on the panel, for example, up to there, we can still see the correlation, right?
Correlation by calculating correlation coefficient.
Yes.
What is the correlation coefficient?
Right. So that's a good question. We are going to quantify the correlation, but not by using the person correlation, but not by using the person correlation, but by using another value that we propose. And I'm going to talk about that in several pages later. Okay. So yes, the key point is the quantification. And when we have quantified the strength of the correlation, we will be able to see if there are correlation or not. So okay, so these are the nice. How many times do I have to? I see. Okay, so these are the real observations, and this is what we have. Okay, so this kind of the red points are actually based on the models with strong phase transitions. And when we introduce the phase transition over there, we're actually introducing more degrees of the freedom. When there are more degrees of the freedom there, then it is more likely for us to break the correlation that we expect. And that is the result. When we introduce this kind of the ambient density jump, then you will be able to construct this kind of the red vertical line over there. And this kind of the red vertical line can easily go beyond the expected linear correlation and touch the high likelihood region beyond the linear correlation. Why is that? Because when we introduce that kind of the strong phase transition, then you will see, as we have already mentioned before, a very sharp turning corner over there. And by introducing that kind of the sharp turning corner because of the phase transitions, what you will see is that the radius of your lighter neutron star will not be influenced by your phase transition, but the radius of your massier neutron star will be heavily introduced by your phase transition, and that will be decreased, obviously. And that's why we will be able to see this kind of the vertical line over there. Okay, so the conclusion, our neutron star radii are correlated. So when we are trying to answer this kind of the question, we have two important observations. The first observation is that about half of the high likelihood region of your nicer observations is lying outside of the linear band that we expect. And the second important observation is that if you are introducing some strong phase transitions with more degrees of the freedom, then you can easily go beyond that kind of the linear region and touch the high likelihood region suggested by your nicer. So the conclusion is that this kind of the observation deviating from the correlation may be a new signal of our phase transitions. And we are going to, we would like to claim that this is a new information that has not been seen by our Bayesian factor. It is simply because when you are doing the Bayesian inference, your Bayesian model really do not require you to explore the whole high likelihood region of your measurements. As long as your Bayesian inference touch part of your high likelihood measurement, then your Bayesian model will not feel any tensions. But in principle and ideally, you should require that your experimental measurement to fully agree with your measurement. And that requires your Bayesian inference to cover the whole likelihood. But that is not the case when you are using some standard equation of state parameterizations. Because
one starts loaded passive, therefore you load the other branch or the other type of outside of
right, yes. So basically speaking, so there are two types of the neutron stars. The first type of the neutron star does not have phase transition at all, and it doesn't include any types of the quarks. And if that is that kind of the neutron stars, then these two neutron star radii point will fall within this linear line. But if you introduce the existence of the quarks, then the radii points of these two neutron stars might be able to fall outside of this kind of the linear band. Okay, so then we go to quantification. So when we are going to quantify that, we need to ask ourselves, is that kind of the correlation unobservable? And our answer will be yes. And because we have already proposed an expected correlation linear regression, and then we can quantify the strength of that kind of the correlation by calculating the distance between a specific neutron star radii point and that kind of the linear regression line. And that kind of the distance is just telling us what might be the strength of this correlation. The larger the distance, the weaker the correlation. So that's what we are trying to quantify our strength of the correlation. So for example, here, the theoretical models, the corresponding distance from these theoretical models are represented by this black contour, by this black probability density distributions. And that red PDF is representing the corresponding distance from our NICER observations. So you see that they are obviously different. The NICER probability density distribution is stretching much longer. And there's a very big difference. So how to quantify this kind of the big difference? So we are using this kind of the concept, which is the probability of identification and the probability of the false alarm rate. So here we introduce this kind of the vertical threshold, where we are claiming that if your observations are falling outside of this kind of the vertical threshold, then you are finding some observations that cannot be explained using our standard equation of state parameterizations. So what's the false alarm probability of that kind of the threshold? So that kind of the false alarm probability is calculated by this kind of the integral equation, and actually it is actually representing the area covered by our black PDF curves on the right-hand side of this vertical line. And if we are deciding our threshold like that, then what's the probability of finding such kind of the observation that is deviating from our predictions and our understandings using the standard equation of state from parameterization? And that kind of the probability is actually illustrated by the area covered by the real NICER observations on the right-hand side of your threshold. So, and that kind of the area is pretty large. It's almost a half. It's 48%. And that means that the probability that suggested by our NICER that there might be some strong phase transitions is actually cannot be ignored. It's kind of a non-ignorable probability. It's almost a half. And how this kind of the new method for phase transition identification can be used for our future observations. So now we only have 2 neutron stars measured by the NICER. But even when we have only 2 neutron stars, this method works because it's a discussion about the correlations. A correlation only requires the data from 2 neutron stars. And if we have more precise measurement of these 2 neutron stars, then the identification power rapidly increases. But what if we have 3? If we have 3, then we have 3 different types of the correlation. If we have 4, then we have 6 types of this kind of the correlation. So actually, the number of this kind of the phase transition detections proposed in this method equals to n-1 multiplied by n and then divided by 2, where n is the number of the neutron stars detected. So in principle, it's kind of like a Skynet for the phase transition detection. So conclusion. So what we are doing is just like a T-Rex-like problem in the sky. And what we find is that this kind of the deviation from the theoretically predicted correlation, what we propose is that this kind of the deviation can be a potential signal for your phase transitions. And how to quantify that? We use a new proposed quantity, which is the distance. And this kind, when we are quantifying this kind of the signal, we find that the possibility of the phase transitions cannot be ignored. So that's our final conclusion. And also, when we are proposing this kind of the new method, it works for 2 neutron stars, and its power will rapidly increase when we have just several more neutron stars. So yeah, so that's the conclusion, and that's some other things that I'm also trying to do. So okay, thank you everyone. I will end it here. Yeah. Yeah, very good question, sir. Yeah, we don't know what will be the maximum mass of the neutron star. So recently we observed something at 2.6 solar mass. Someone say that is a neutron star, someone say it is not. We don't know yet. But anyway, so yeah, that definitely helps because I don't know if I can move back forward faster. This is too frustrating. Oh, sure. Okay. Yeah. So, okay. Yeah. So the answer to your question, sir, is that the information of the maximum mass of your neutron star is determining the maximum or the minimum radii of the neutron stars, as we can see in this figure. So when they are going to draw the branch of the minimum or the maximum radii of your neutron stars, it depends on the maximum mass of the neutron stars. So actually, this gray branch is assuming that our maximum mass of the neutron star is 2 solar mass. But if we assume our maximum mass of the neutron star is 2.6 solar mass, then the minimum radii branch will be this purple one, no longer the gray one. So which means that if we know more information about the maximum mass of the neutron star, then our information about the maximum or the minimum radii of the neutron stars will also correspondingly change. But right, yes.
0.1 versus.
Yes. Right. So that is one backup point. So we're trying to discuss the possible influence on that kind of the because of the unknown maximum mass, right? So if we assume the maximum mass is 2.0, then we have a linear regression line. If we assume the maximum mass is 2.6, we have another linear regression line. So how different they will be? So here we are plotting these 2 linear regression lines together in this figure, and it seems that they are almost exactly the same. So the conclusion is that although the maximum mass of the neutron stars is tracking the branch quite obviously, but if we are extracting the maximum and the minimum radii of those neutron stars, and draw this kind of the linear regression, the slope really doesn't change too much. They're almost the same.
I remember when the slope, the number you put, the 48%, like 50-50, whether it's a phase transition. If you knew the maximum mass of the neutron star, that changed that percentage to very
No.
much.
So currently, my answer to your question is no. Because I mean, this kind of the changing or the update of the information will slightly change this kind of the linear regression line. And our 48, that 48 number is depending on the distance between the point and that regression line. If this regression line doesn't change too much, then the distance won't be changed too much. Yes. Okay, sir.
Question is, start with simple equations of state to get a correlation line, when you start from simple equation of state to phase transition. What about just more creative equations of state without phase?
More creative equations of state. Yeah, so then we need to think how to define the creative.
Creative just more complex.
Yes, right. So that's why so that's why what we are claiming is that we find something beyond the standard parameterization. So we cannot specifically say what's outside of that standard thing. It's just like, when we are discussing something beyond the standard model, we only need to ensure that we know enough information for the standard model. We cannot say that we know everything beyond the standard model. Yeah.
So down your top was
Right.
basically from nucleonic matter to quark matter.
Yes. Right.
But don't we expect several?
Yeah. Yeah. That's also possible. Yes. Yes.
Several.
So yeah. So this will not impact our picture a lot. So. Okay, when we have several more phase transitions, in principle, that is introducing more degrees of the freedom in our equation of state parameterizations. So naively speaking, when you have more degrees of the freedom, then it is more likely that kind of the correlation will be broken. So in this way, I will expect that if you have several more phase transitions, then that kind of the equation of state parameterization with 4 phase transitions will also give you a posterior distribution that might, part of them will be falling outside of the linear band. So that's my expectation. So yeah, but here, what we only require us to do is try to figure out what will be the posterior distribution without any phase transitions. So when we know that, and then we see the observation, we will be able to figure it out if there are phase transition or not. So yeah, so that's the basic logic upgrade. Yeah. Yeah.
One of phase transition at a density of like 4 times saturation density.
Yes. Good question. So where does the phase transition happen? So that's a question we want to answer. So if we see a broken linear correlation, then we might be able to expect that that kind of the correlation is happening approximately between the central pressure of that 1.36 solar mass neutron star and the central pressure of that 2.0 solar mass neutron star. That's in that way, approximately, we might be able to identify the location of the phase transition. But this is a correlation method. I mean, the detailed information from the phase transition cannot be precisely extracted from that. To do the detailed study of the phase transition features, we still need Bayesian. But here, this is the method beneficial for us to identify if there are phase transition or not. Yes.